In this unit, we're going to be looking at two new topics. One is an integration technique called integration by parts, and the other is an application of integration where we use integrals to find the average of a function. We're going to start by looking at the integration technique, integration by parts. Reminder of where we've been already. We've looked at direct antiderivatives or integration when we have relatively simple functions, and that would be cases like the integral of e to the x or the integral of cos of x. Those we can find an antiderivative just by knowing our derivative rules. And we also covered the second approach or second method, integration by substitutions, and those worked for cases like x over root of 1 plus x squared, or the integral of x squared e to the x cubed. Those were cases where we saw one function inside and its derivative ready to be cancelled when we use a substitution. Unfortunately, that does not cover all the cases, so we're going to introduce a new method now called integration by parts. This would be a classic integration by parts example where substitution would not help. The only obvious substitution here would be either w equals 4x or w equals e to the 4x. And neither of those lead to simpler integrals. And if that's the case, then our substitution simply doesn't help us at all. You can try it if you like. The key ingredient that we're missing in these cases is that the derivative of 4x or e to the 4x is not there waiting to be cancelled when we replace the dx with dw. If this had been an x squared, it's important to see the distinctions. If this had been an x squared, yes, substitution would have worked perfectly. But that's not the integral we were given, so we can't do that. So that inspires us to look for a different technique that might help us find an antiderivative of this complicated product here. Okay. The rule of integration by parts comes from the product rule from derivatives. Let's take a look at how that might be written out. If we had two functions u and v and we had their product, then their derivative would be the derivative of the first times the second plus the first times the derivative of the second. Now if we integrated both sides of that, because that's a nice rule for derivatives, but it doesn't help us with integrals. If we integrated both sides with respect to x, what could we get? Well, this right-hand side turns out to be not particularly helpful. We're going to write this as u prime here, just for the sake of clarity here. And actually, I'll probably write it as v u prime dx. And this one we'll write as the integral of u v prime dx. The interesting part's on the left-hand side, because I think what we've just done here, we've differentiated, and then we have anti-differentiated. And surprise, surprise, when we differentiate and then anti-differentiate, we get back to what we started with, u times v. Okay, so what does that leave us with? Well, what we can do is focus on picking arbitrarily one of these two integrals. We're going to pick this one here. We can say that the integral of u dv dx, or u v prime dx, can be written as u times v, and we're going to bring this other term here, this other integral, to the far side. It'll become negative, and then we'll have the integral of v du dx with respect to x. And we're going to play a little fast and loose in a second, but the key thing is we have an integral, and it's equal to some function minus another integral. That's very similar in flavor to substitution, where we traded one integral for another. Here it's just a little more complicated with extra terms popping in. Here's a short form of this formula that you'll see everywhere in textbooks, the web, references, tutorials, and it's the integral of u dv. So essentially what we had before was dv dx, and then we integrated with respect to x. So we play a little fast and loose, treating these as deltas here and canceling them. It makes for a nice short form. It's not maybe the most robust theory behind it. But the integral of u dv is uv, and the key thing here is no integral for this term, minus the integral of v du. Okay, how does this work out? So this is the formula, memorize it. Integral of u dv equals uv minus integral of v du. Repeat that 10 times, it'll get stuck in your head. How does it help us actually evaluate integrals? Well, we're going to take what we were given, so this is our given integral. We're going to designate part of it as u and the rest of it as dv. So this is not substitution. In substitution, we can pick just one part as our substitution and then move forward. Here we're going to have to take the entire integral that we're given and break it into u or dv. Every part has to go into one or the other. What we're going to do then is differentiate the u part and integrate the dv part to get v. That'll give us the two missing ingredients here. Here we have a dv, but we need a v. The integration will get us that. We also have a u, we need a du. The derivative of u will get us that. Finally, we're going to hope/check that the new integral that we get, this integral of v du, is somehow an improvement over our original. So refer back to this as necessary. It's easier, I think, though, to see it in practice with an example. Let's take this x e to the 4x integral as our first case for integration by parts. So let u equal x and dv equal e to the 4x dx. So this is a division. Everything from the original integral is now either in u or it's in dv. One of the natural questions at this stage is why pick those? We'll get to that after we do this example. Suffice to say, this is a good choice and it will lead to a simpler integral for now. Our next step is to fill in some relationships. We have u, but we need du, so we're going to differentiate this on both sides. And we're also going to integrate both sides of this. And we'll see what we get. So we're going to get du dx is equal to 1. Or we can rewrite that as simply du equals dx. So that's one of the pieces we need. So we just take the dx up, and we get that relationship. We're going to need u equals x, and the other one we're going to need, once we integrate this, if we integrate 1 with respect to v, we're going to get the variable v back, and then the integral of e to the 4x is e to the 4x over 4. Now one of the concerns might be that we need a plus c, because we did integrate from here to here. As we'll see as we go through some examples, it's not necessary because we still have an integral to evaluate. And if we still have another integral to evaluate, then we can put the plus c later. And it can wait until the final integration step. All right. Now, if that's the case, then if we look at the symbols used in the integration by parts technique, we have u, we have v, and we have du. Going back one step, we have u, we have v, and we have du, so we can start filling in the entire integral that we had before. And the nice thing, if you're consistent about the layout here, and we'll try to be consistent as possible as we go through these examples, then we have the integration by parts as u times v minus the integral of v du. It'll always occur in this layout, uv, v du. And that makes the integration just a little easier to keep the bookkeeping straight. So if we have the integral of e to the 4x dx, and reminding ourselves that this is our u, and the other half was what we were going to call dv. Now we apply the integration by parts formula, and we can then rewrite our integral as just u times v, so x times e to the 4x over 4. That's our u and v minus the integral of v du. So our e to the 4x over 4 times dx. That's our v, and that's our du side. And that's it. That is one step of integration by parts. What we've done is traded one integral for another, and the question we ask ourselves is the new integral better, simpler, easier to evaluate than the one we started with? Absolutely. This one had a product, and it's really hard to infer reverse product rule type things. This new integral, though, is simply an exponential. So this is simpler, and we can actually evaluate it in one step. So we can now do another antiderivative and evaluate it immediately. So we'll get x e to the 4x over 4. We'll simplify that a bit. X e to the 4x over 4 minus, now I got to be a bit careful here, I'll do it in two stages. 1/4 e to the 4x dx. And then we're going to do the integration, so we keep this term the same, x e to the 4x over 4 minus 1/4 the integral of e to the 4x. We have the 1/4 from before. This integral, e to the 4x, also gets another 4, and then we get a plus c at the very end. So the plus c at the integration by parts stage, not necessary, because we're going to integrate later, and we can add the plus c as the very last thing in our final integration. So we started with the integral of x e to the 4x with respect to x, and we come up with this term here, and we might want to know that this is actually right. We'll see that in the next page. Verify that our antiderivative is correct. Well, our claim is that the integral of x e to the 4x with respect to x is x e to the 4x over 4 minus, when we combine those fractions, we get e to the 1 over 16 e to the 4x plus a constant. And how do we check? We're going to take the derivative of this term here. We're going to find the derivative with respect to x of x e to the 4x over 4 minus 1/16 e to the 4x plus a constant. That is equal to, all right, product rule here. So as we see with the integration by parts rule is product rule based, it's not a huge surprise that the product rule will be involved when we check our answers as well. We'll have 1/4. We'll bring that out front. The derivative of x is 1, and then e to the 4x is itself, plus x times the derivative of e to the 4x, and that's e to the 4x times 4, minus 1/16 times the derivative of the exponential, that's e to the 4x times 4. And the derivative of the constant is 0. All right, let's simplify that a bit. We'll have 1/4 e to the 4x. Then the quarter and the 4 here cancel. We'll have plus x e to the 4x minus 4 and 1/16 is 1/4 e to the 4x. And we notice, this is great. That and that are equal but opposite signs, and so we get x e to the 4x. So this complicated expression here, when we differentiate it, comes back and equals our original integrand, and that's how we check any integral. Big check mark there. Integration by parts for this particular example works its way back to being verified. So the antiderivative of x e to the 4x is in fact x e to the 4x over 4 minus 1/16 e to the 4x plus a constant.